This manual will take you through step by step of taking that original mix design and adjusting it into your mix design. And what they do here is you keep the mortar fraction of that mix design. I won't go through, I don't think we go through step by step here. I guess we do. These are the specifications. In this case, this was for a bridge deck. But just to give you an example of the step-by-steps, these were the specs that you had to meet on the mix design. And instead of going to a high-rise building, they picked out a specification, a DOT bridge deck in Colorado. And they looked at all the cementitious components first. Whether it's high strength or a bridge deck, it's the same steps that we go through. They took those, the materials, the cementitious materials for that high performance concrete, and added your own local aggregates to it. Your own aggregates have their own specific gravities. They have their own volume. So you have to match that up. The cement, silica fume, and fly ash, their specific gravities are pretty much universal across the whole country. They don't change, but your local aggregates will. So you add your local aggregates in to balance out your proportions. I won't go through the details because you guys don't need to do that. But when you go to a laboratory and actually make this concrete, there's a ASTM specification, it's called C192, that is very precise on how you make concrete in the laboratory. Well, the problem is C192 was written back in probably 1965, before any of this technology came around in the early 70s. And so following C192 in the laboratory, you may not get the high performance that you're looking for out of the concrete. So the manual goes into detail here of if you're going to make concrete or high performance concrete in the laboratory, these are the steps to go through. It's a little bit different. Really, it involves longer mixing. Laboratory mixers aren't real efficient compared to big truck mixers where you have 4,000 or 40,000 pounds of material tumbling around and mixing. Lab mixers are relatively small and there's not a lot of energy in there. So there's a lot more mixing here compared to the ASTM test method. But the mix design specifications for the 100 years, the Bureau, the Water Bureau said they wanted 10,000 PSI in 56 days. That's the age of the concrete. Because this concrete was going to be exposed to freeze thaw at least for the first year before it was submerged back underwater, the concrete need to be air entrained. It's where they actually put in literally soap bubbles into the concrete, making very, very tiny small bubbles to give the water in the concrete the moisture that's left over in the gel. When water freezes, it expands 9%. And what this air entrainment does is give a place for that freezing water to expand to without breaking the concrete. Any concrete exposed to freeze-thaw conditions, whether it's driveways, sidewalks, curbs, if it's outside, it's probably going to be air entrained concrete. The guys in the laboratory gave your construction crew the mix design. Their laboratory mix, they achieved the specifications. They were able to achieve 11,000 PSI out of this concrete in 56 days and had 5% air. So this is what you know is going to be made on your job site, and this is what the mix design looks like. They put in 700 pounds per cubic yard of cement, and because of the location of this, we couldn't bring in all the materials to make we couldn't bring in the fly ash and the slags and those type of things you would use. So they just went with one pozzolan material. In this case was a silica fume. Water cement ratio, has anybody ever heard that concept? Water cement ratio? The lower the water cement ratio, normally the higher the strength. Typical concretes in a driveway will be 0.45, maybe 0.5 water cement ratio. And it's really what it is. It's the amount of water to the cementitious materials, which in this case is these two combined. So we'd be looking at the cementitious factor would be 780. The water would be, what, 250 pounds of water, something like that, using that ratio. They incorporated the local materials, both from California. Caltrans approved limestone, Sacramento sand. Air entraining admixture was a product called Micro Air. They used a water reducer to make this concrete. And they were delivering a slump, at least in the laboratory, they were delivering a slump of 6 inches, which is fine. That's something we can work with. We can move around by hand because we're not going to do this with pumps and stuff. But when we take it out to the pump station, the guys call into you and they say, we got a problem. Our high strength concrete is setting up too quickly. Setting up means I can't get on it. I'm trying to place it and you know, I can't move it. It's getting hard already. They're talking about within 30 minutes after batching, this stuff can't be pumped. They can't move it into this pump station. They can't pump it through there. It's starting to set up, is all you know. This is what you know about the project site. It's called Cherry Lake. You're at about 6,000 feet in the Sierras in late September. All the materials, because of the remoteness, remember you're on the edge of a national park, so there's no quarries or roads, or you know, you're probably an hour and a half away from nothing. So all the materials have to be trucked into site. The structure is going to be underwater for life, so we need that 6% air and train for a freeze-thaw exposure here. And our goal, or your goal here, over the next little period, is to try and figure out what happened to that concrete. To try and figure out what could have possibly happened to that concrete that, you know, when they made it in the laboratory, it was 6-inch slump, it had flow to it, it had moisture to it, it had things. When they made it out in the field, it was drying up. They made it and it was wet, and in a matter of 15 minutes, boom, it was gone. It was dried up. They couldn't move it. It was, you know, like a block mix, real dry to the hand. You couldn't even make a ball out of it. It was drying up that quickly. You go on to site, and this is what you find. The dam's been lowered down, the water's all exposed, or the rock's all exposed. That's the pump station that's going to be built. The tunnel leads back up into Hetch Hetchy, and you can see the tunnel here. So this is one part of the construction site. Most of your crew lives on site because of the remoteness. That's another location. Another shot of the pump station, some of the material around there. That's your batch plant. Got a couple little trucks here. One batch plant, they trucked in the materials, the limestone and the sand, everything's all right there. Can't use the water from here though, because that's potable water. So you actually have to truck in your own water from there too. It's a national park. Another shot of the batch plant. A couple different shots of the batch plant showing its isolation. The pump station is actually right here, behind these rocks, where the construction is. So they're talking about trucking this material from here to here, and they can't get it out of the truck. They made it in one place, and they can't get it out of the truck in the other place. They've got the mix design here. They know it works. You're on the site. There's no help. You've got to come up with an answer of what happened? Why is this stuff drying out? And there's a trick to how you do this. And anybody ever know how you come up with the right idea? You come up with a lot of ideas. And somewhere in those, a lot of ideas will be the right idea. So what we're going to do here in the next 5-10 minutes or so is we've got enough people to break up in at least 3 groups. You know, 5 or 6 in a group, in the back, in the center, up front. And the idea is to try and come up with as many ideas. Nothing's far-fetched, nothing's off the table. What could possibly have made that concrete dry up in 10 minutes, 15 minutes time? Where do we start? Where do we start on this? Count off 6. You got 6 in the back? Yeah.
Maybe the temperature?
Put it down. Everything counts. The idea here in the next 10 minutes is to see if you can come up with at least 10 to 15 different things that could have gone wrong. Everything counts. I mean, in a group, I want you to work together in a group and talk this over. And somebody make notes, because we're going to talk about some of these ideas that we come up with here. But the whole idea of this exercise here is, again, to come up with the right idea, come up with a lot of ideas. Everything counts, from sabotage to you make it up. 4 or 5 in the back? Yeah, 4 in the back. You guys know each other, man. Get together. 3 groups. No, you need, yeah, we got 1. Why don't you guys move over here? You 5, and then you 2 over here work with those guys. Yeah, there you go. There you go. No bad idea at this point. No off-the-wall idea at this point. Only way to come up with the right one is to come up with a lot of them.